So good afternoon, everyone. Thank you for joining us. This is our last session, our last talk of this SGT, or Society of Glass Technology Christmas lectures that we decided to organize to promote the Society of Glass Technology. And today we are here to listen to Russell Hand, who is going to talk about the durability of vitrified nuclear waste and analog glasses. Russell is a professor at the University of Sheffield, and the presentation will be about 20 minutes. So Russell, first, thank you so much for accepting this invitation from our side to be here today and to present a little bit of this part of your research. And whenever you want, we are ready. Thank you so much.
Thank you, Inês. So, welcome everybody. I know there are several people on this call whose work may feature in this talk, because what I'm going to talk about is some of the work that we've been doing on looking at nuclear waste and vitrifying it, and how you might study that to understand its long-term performance. And I've just got my mouse on the wrong screen, so the slide didn't go forward. So I could have put many more names on this than I have done. The names that actually appear on this slide are people whose work or have contributed in some way to the work that's being presented directly here today. But there are many other people, notably people like Paul Bingham, who's on the call, who've been involved in the work that we have done at Sheffield over the years. And without all of these people, this simply would not have happened. And equally, without all of these various agencies, both in the UK and overseas, funding us, the work would not have happened. And I should also particularly mention Ballard and Quarry, owned by Tarmac, simply because some of the data I referred to relates to glasses that are actually buried there on their site. However, where I'm going to start is why, in one sense. Why are we worried about nuclear? Well, fundamentally, we're talking about large scale of electrification of industry, as well as other things in the next few years. Stuart last week was talking about electrifying blast furnaces. Unfortunately, I was not able to be present for that. But there is an implication. If we go for large-scale electrification of industry, transport, etc., we are probably going to need to generate more, not less, electricity. And we clearly need to move away from burning coal. We have a picture here showing the Drax power station, which was originally a coal-fired station, is now a slightly smaller biomass station. You can argue about whether biomass is a good idea. But, that's producing gigawatt levels of power. If you look at the alternatives, a large-scale wind farm, it's still only in megawatts. A fairly large solar array that you can see from space, still only in megawatts. Concentrated solar, this is a tidal barrage. The one real exception to that, which is not nuclear, is hydro. And this picture of the largest hydro scheme in the world, which is the Three Gorges Dam in China. There are all sorts of environmental implications going for hydro, but you can generate a lot of electricity. We are going to need additional baseload electricity. In other words, things that can always be on, that's reliable. Nuclear, at least in the foreseeable future, is a necessary part of that picture. And the picture at the bottom there is, I think it's from last year, but it's Hinkley Point C, which is showing something of the sheer scale of the construction to produce a 3.26 gigawatt power station. So nuclear is going to be essential in future, and clearly it's had a long history. Now, why is nuclear essential? Well, it's actually quite useful just to have a look at how much energy we can get from nuclear. So if you actually look at how much U-235 that we require to produce 3 gigawatt a day's thermal energy, which is effectively about 1 gigawatt day of electricity. You can go through a formal calculation. I won't go through every step just now. That's not the point of this lecture. But effectively, when you break 1 uranium, you get about 200 MeV out of it. And when you work that through, that doesn't sound like very many joules. It's 3.2 times 10 to the minus 11. And 3 gigawatt hours is more like 2.6 times 10 to the 14 joules. Sounds like a big difference. But if you actually work out the number of fissions you need, or rather the mass that you need of uranium to do that, uranium-235 note, it's about 3.2 kilograms. Now, uranium-235 is the uncommon isotope, so there'll be a bigger mass of uranium that you're using than that, even if it's enriched to, say, about 5% U-235, but it's still a small quantity. Just to get to the same level, Drax was slightly bigger in terms of electricity, but it was burning 36 million tons of 36 million kilograms of coal a day. So the sheer scale of the energy you can get from nuclear means that there are some very real advantages to having nuclear power stations. Yes, they're a big piece of infrastructure. Yes, they are expensive to build. Yes, we have to take appropriate safety precautions, but we can get a lot of energy from them for relatively small masses of material. Now, when we actually have a nuclear power station, of course, what's actually going on is as I've already indicated, we're having fission of uranium-235. There are a couple of example equations here. They are only examples because what happens in fission is you get 2 unequal bits across the middle of the periodic table. Those bits, the fission products, often are not very stable because they typically have too many neutrons. They might be gases, they might be what we call neutron poisons. They actually compromise the ongoing running of the reactor. They can cause structural changes in the fuel. And at some point or other, we will have to take the fuel out of the reactor. You can then have what's called an open cycle where you'll send the spent nuclear fuel, the SNF, to disposal, or you can have a closed cycle when you can reprocess the fuel, extract the uranium that's not been used, the uranium-235 that is in particular, although you will also get the 238, and also typically you will also extract the plutonium as well, although that gives rise to other concerns. And the UK in particular has in the past reprocessed its fuel. At the moment there were no plans to do any further reprocessing, but we have reprocessed the fuel in the past. And one of the consequences of that is you get what is called high-level waste. This is highly radioactive waste. It contains many of those fission products that I've referred to. There are 2 in particular that you might have heard of in terms of their environmental impact, cesium-137 and strontium-90. They're particularly common. They're beta gamma emitters, and they're heat generating. So they are particularly problematic. I put the word short term there because they're radioactive, they have a half-life, and after about 10 half-lives, you typically would say you don't need to worry too much about them. 10 half-lives in their case is about 300 years. And in the UK, this high-level waste that we produce from fuel reprocessing has been turned into a glassy waste product. There are 2 pictures of glass on this slide. One of them is a natural glass, namely this one. This is actually an obsidian, and that sample is about 5 million years old. So it gives you an idea. We can have confidence that glass can survive for a very long time in the natural environment. The sample at the bottom is an inactive, so chemically identical essentially to the vitrified nuclear waste, but containing no radioactive isotopes. Sample from, I think it was Line 3 commissioning at Sellafield, although that might be from a different source, can't quite remember now. And then there are other waste that we might vitrify. But fundamentally, if we're going to vitrify waste, what we need is a glass that can dissolve the waste elements into it, bond them in at an atomic scale. We want things with relatively low melting temperatures so we can process them easily. That's not totally compatible with high chemical durability, but fortunately for borosilicates do give us a reasonable combination of those two properties, that we can generate borosilicates for this process, which can be remelted and incorporate waste at about 1050, 1100 centigrade, but have decent chemical durability once the waste is incorporated. And we're going to, because we need them to last, and we need them to last on the sort of timescales these obsidians have lasted. So what will we do with this material once we made it? Well, initially we'll store it above ground for decades, probably longer than we ever intend to. The current store has a design life of 50 years. It's going to need to last at least 100. But eventually they should go into some sort of deep underground disposal, where we will dig down, say, greater than 500 meters, probably down to about 1 kilometer, and build a set of vaults into which the canisters of glass are then placed. Those canisters of glass will be surrounded by a clay backfill, and eventually, of course, you've got the rock barrier, which gives you your fundamental isolation from the environment. So, why do we need to worry? We're burying this glass at 500 meters, kilometer depth. Surely, if we isolated that much, we don't have to think about it. Well, at one level, the rock barrier should mean that things never get back to the surface. But obviously, to make a good safety case, we should actually consider what happens when water does reach the glass. Because we can guarantee eventually all of the barriers will gradually fail. Water obviously does go through rocks. We've seen plenty of examples of that. It will eventually get through the backfill, the stainless steel, the glass will eventually see it. So we then need to think about, well, how do we model this glass? Well, we can do laboratory experiments. Now, they are good for controlled conditions. Many laboratory experiments are relatively short, a few days, a few weeks, even a few years. But it's not very tempting to a PhD student to say, we want you to do a durability experiment lasting a decade or two, and you'll have to wait that long to write your thesis. So necessarily, a lot of things happen on a relatively short timescale compared to the timescale we're interested in. So what other things can we do? Well, we can look at archaeological glasses. These are things that humans made, and therefore we can have some confidence, perhaps, that they're a bit like the things that we're going to make with nuclear glasses, although typically they will have be made without a knowledge of the chemistry that we now have. And then we have also the natural glasses. I've already mentioned obsidians. In fact, obsidians are known out to about 100 million years. It's assumed they probably crystallize on timescales greater than that. The one issue with obsidian, or what basalt, which is actually a closer analogue, is that none of the natural glasses contain boron. And virtually all of our nuclear waste glasses contain boron. But nonetheless, we can do experimental studies on our nuclear glasses. We can then look at natural and archaeological glasses in the lab as well. So we can sort of look at how those experiments relate, and then we can compare that to what happens to the natural or what has happened to the natural stroke archaeological glasses in the natural environment, and try and combine all of that together to do some useful long-term predictions. And that's really what I want to touch on today. So in particular, I will touch on some stuff we've done with basaltic glasses and some work related to some archaeological samples that have been buried at Baladin. So that's a sort of analog experiment, actually. Right, I need to keep an eye on the time and where I'm going. I think I might skip that slide just now. So, basaltic glasses. We made, no, not basaltic glasses. First of all, co-location, so impact of high pH. So these are some glasses where we've done some studies on calcium aluminoborosiliciates. We did also study a basaltic glass as part of this work. But it just shows some of the complexities of what's going on. So the first sort of thing we did here was, because this was to do with possibly co-locating cemented material with glass, we were actually worried about high pH conditions. We did that by looking at what happened if we put the glass in potassium hydroxide, where we didn't see any alteration layers on the glass surface, except when no aluminium was present. And you can see that we could see that there was definitely attack on glass. We also saw some very strange, severe localized features. We presume that originates from a pre-existing defect, although we do not have a definitive explanation of why we get these at this stage. And okay, I think I'm going to skip those slides, apart from just showing again the complexity here, the alteration layers we get on the surface. So one of the things that we find is you do see different alteration layers on the surface. Sometimes these are fairly uniform in composition, but quite often we get things like this. We get banding, as if we've got some sort of cyclical type process. Now, in an example like this, that cyclical process looks like it might be fairly obvious at a regular cycle. In some of the other samples we have, it's not clear from different time points whether there's further alteration that happens, so it's not quite a simple cyclical process. But the bands have different chemical compositions. And we've seen this in quite a variety of cases now. And again, in terms of fully understanding what's going on, we need to look at these sort of phenomena. We see similar things in some of the archaeological glasses. Right. We also see crystalline alteration products on the surface. These are very dependent on glass composition. So this is a UK nuclear waste glass that's been in calcium hydroxide for 720 days. We can see various crystalline alteration products on the surface, or partially crystalline. These are essentially cementitious-like, what we call CSH type gel. And we also see some other phases involving magnesium, as well as an iron hydroxide phase. Basalt under the same conditions gave very different crystal structures, but again, there was a sort of calcium-rich, more cementitious layer on the outer surface. Okay, here's the basaltic glasses where we deliberately varied the magnesium to calcium ratio, and this is the work of James Mansfield, who I know is on this call, so thank you, James. And having varied those particular ratios, we're concerned about those ratios in this country because the UK has magnesium-rich glasses arising from the type of reactors we used to run, which were the Magnox reactors. So we looked at the long-term durability, or longer-term durability, both in what's called a PCT test, a powder test, and you can see here that essentially initially you get a fairly rapid release and then things slow down. And we've looked at the amount of silicon going to solution, the amount of lithium going into solution. This one shows the pH. But effectively, in all cases, there's initially rapid release, then it slowed down, and then there may be a bit more of an acceleration again. And that's, that's potentially a bit of a concern. However, the longer-term tests still, so we're using monolith tests and running out to 672 days. In the case of a couple of samples, we also have them going out to 1800 days. You can actually see that things do overall flatten off fairly well. might be a bit of an uplift towards the longer times, but there's no evidence that things really accelerate again. So it's longer term data, but it's still quite limited. It's what you can do in a laboratory, involving, well, one person setting up the experiments. Those last two data points were actually analysed by somebody else. We can also see alteration layers on those glasses. They vary according to the glass composition, and there's some evidence that we saw more precipitates on the higher magnesia glasses. There's more slides on that, but I will skip forward just to look at the average layer thickness. Generally, the thickness of that alteration layer increased with magnesia content, so that's something we'll have to think about for UK historic glasses. But for certainly the lower magnesia content glasses, the layer thickness looked like it plateaued even out to 1800 days. And when we compared the thicknesses of those layers to data on basalts from the environment, what we generally found is what we were getting in the laboratory was, if you like, something of a worst case scenario. What appears to happen in the actual environment takes much longer. Which, that's the way, if we're going to be pessimistic from our laboratory experiments, that's arguably a good thing. We don't want to be too overly optimistic. Right. I'll say a little bit about Baladin and a couple of things from it, and then I suspect I'm going to have to wrap up because my time seems to be ticking past quite quickly. So Baladin is a modern version of a burial mound. There are various burial mounds in the UK with different materials in them. And there was originally a sort of model experiment set up by archaeologists at Overton Down in 1960, but that didn't include glass. They then set up a similar one at Wareham, which did include glass in 1963, but that was low pH. And not a lot happened to the glass, certainly initially. So in 1970, a high pH environment, some glass samples alone were buried on the edge of the Baladin Quarry. And it was a triumph of optimism, this particular experiment. The samples were supposed to be dug up every 2 to the n years, starting at 1 year and going out to 512 years. If anybody cares to volunteer to dig up the 512 years samples, you'll please come forward. So, obvious challenges with continuity. Roy Newton was involved with the experiment. This showed he devoted despairing paper in about 1985 that nobody remembered to dig up the 32-year samples. Actually, who was present for digging them up? He was aged 89 at the time, but he was able to actually attend the digging up of those experiments. The site also changes. This picture here, that tree, I think, is the large fir tree in the background in the other picture. They're definitely taken looking in the same direction. Okay, so there were various glasses buried at Baladin. Originally, none of them were nuclear glasses. Some were model archaeological ones. Some were modern glasses. Note there is no float glass here. Because it's based on the Wareham experiment, float was a novel material at the time, and in fact, it was plate that was buried. And we've now got some weather records. But yes, just to sort of tie this off by looking at some of the experiments, this particular work of Gary Manifold and Claire Thorpe. So these are the samples as they were unearthed. And then starting to look at the cross sections, and particularly the Hangleton linen smoother, which is a glass. The original version of this was buried in a house fire and was known to have been buried for, I think it's 266 years, and it has lots of layers on it, which is one reason that people were interested in it. Generally, the less durable potassium-rich magnesia glasses, the medieval one, the Hangleton linen smoother, have thicker layers on them. There are some interesting features on the plate glass, these sort of vermiform features. It also appears on pyrites. We think this is probably due to localized chemical attack arising from sort of stress corrosion linked things, but we have yet to prove that in a definitive fashion. And then also some layers on lead optical glasses. Note that we only see the sort of localized features on the most durable glasses where there is not huge amount of change in the glass surface very quickly. Right. Okay. So that's some work done a few years. What I will just skip to is just sort of showing some evidence of the sheer number of lines, the sort of variation that we do actually see on the surface. So we get this banding, which is chemically complex. You can see the silicon concentration varies. This is the actual glass down here. And as you come away from the glass, you can see variations in the silica content, reduction. The potassium's essentially all been removed, and some of the other alkali species have essentially been removed. But then there's banding in the surface, which includes elements that actually come from the soil, not from the glass. And some of what's coming out of the Baladin work is indicating that not only do we have things diffusing out of the glass, we have material diffusing in. Now, Baladin is not an analogue of a deep repository. It's a near-surface burial in the UK. It sees quite a lot of rain. That's not how a deep repository is going to react, where you've got effectively, essentially, largely stagnant water. But we do have evidence for this we do see these chemical bands. We're trying to fully understand how they occur, what concentrates where, and why. And it's this sort of analog experiment that's going to be useful in helping us predict the long-term behavior of some of these waste glasses in their disposal environment. Given it is now virtually 2 o'clock, I think I will stop at that point. I do have plenty of other pictures if people want to see some other pictures, but I think that's the major message I wanted to get across. So thank you.
Thank you so much, Russell, for this interesting talk. I have questions, but before I ask my questions, I would like to open the talk and to see if someone wants to ask any questions. You can just unmute and ask, or if you prefer, you can write on the chat room and I can read out loud the question. So I think while people think a little bit about questions, I can ask my question. So Russell, I was wondering if during your studies and characterization of the degradation of all these glasses, did you ever look into the trace elements? So is there any change besides the obvious and expected change in the major elements during degradation? Do we know what happens to the trace elements?
Well, we certainly know that things that are there in relatively small quantities can make a significant difference. So actually, something that I glossed over because of time is, in this particular case, so this is a glass known as ISG, which is a relatively simple composition. It contains about 2% zirconia. These bands are alternating zirconia-rich, zirconia-poor. This glass contains about 1% zirconia. We don't see zirconia-rich, zirconia-poor bands. Now, it's a more complex composition. There's more things going on. But this is not the only example where something that's there in relatively small quantities, the amount seems to impact the overall behavior. On some other Ballard and Expat samples that are actually more representative of nuclear waste gases, I think I have a copy of the slide on here. Yes. We are actually finding concentrations arising from relatively small quantities of rare earth elements on the surface of the glass. So again, we've got evidence that something that's there, not necessarily in large amounts, is participating actively in what is going on. We cannot just look at the majors.
At the major. Now, I was actually thinking about the rare earth elements because it's something that usually when we think about studies on degradation is something that I noticed that we are lacking. Is there information on what happens to the trace elements and especially or more specifically to the rare earth elements? Thank you. So we do have a question on the chat.
Okay, so James is asking about the basaltic MCC1 experiments I talked about. We've certainly looked at 2 of the samples that you left ongoing because they were the 1800-day samples. I'm not sure if there are any more still going, and I certainly know that those 1800-day samples, there had been more water had evaporated than was ideal from the actual test pieces.
Thank you. Paul?
Thanks, Inês. Thank you, Russell. Fantastic presentation. Just thinking out loud here, really, but you showed that the very, very strange vermiform, sort of localized tunneling, kind of almost like drilling effect. And you mentioned potential stress corrosion behavior. I guess just as a sort of a general sort of philosophical question, how worried should we be given the way in which high-level waste is poured into a canister, cooled, and then has more hot stuff poured on top of it, creating lots of cracked surface?
When we took, and James actually did a very thorough study here, so he actually went round his monolith and effectively measured the number of features that we had, and we worked out what the implication was from these cross sections for the overall sample. And although there was a notable increase in surface area, it wasn't sufficient to cause a fundamental problem. So it's sort of one of those things that sort of interest scientifically, but not something I think we really have to worry about for disposal.
That's good to know. Thank you.
Thank you. I don't know if anyone has other questions. If not, I think we should again thank a lot Russell for accepting to give this final Christmas talk series. Thank you a lot for everyone who attended. And I think it's important again to refer that these talks were done within the scope of the Society of Glass Technology, and that our main aim is to increase the number of memberships, so please do visit the website. And if you have any doubts about how to join the SGT, everyone by now has my email, so you can email me and I can for sure help in any way that I can. So thank you a lot, everyone. Oh, there is Lisa asking or commenting. Lisa Holland says, I always find vermiform formation and alteration layers fascinating. They are actually. And we should know a little bit more about that. So thank you all so much. Have a great break. I hope everyone has a few days to rest in this end of the year. And again, thank you so much, everyone, for attending the talks and for all our speakers, Russell and Stuart last week. Thank you so much.
Great.